Hello. Hello. Yeah. I hope I am audible to you. Mic seems to be working fine. Yep. Okay. Can just- Okay, mic is fine. We'll just start the recording. Recording is started. Yeah. Okay. Mm. So, a very good evening to everyone. Welcome to today's live interactive session on geology and soil mechanics. So, welcome to the 7th week of this interactive session. So, already almost we have covered half the distance of this course. We have covered half of this course, and the other almost half is left, right? So 50% of this course has already been covered, and the rest of the 50% is remaining. So before we begin today's session, if you recall what was taught in the previous session, started the topic of consolidation. So we understood what consolidation is, right? And under what circumstances consolidation actually takes place. So in case of consolidation actually takes place, consolidation settlement, if you want to say that, consolidation settlement or consolidation phenomenon that occurs in a saturated soil. In a saturated soil, especially a saturated fine grained soil, there we see this phenomenon of consolidation, right? So we understood what consolidation is, how consolidation takes place, right? And uh, we learned how the uh, uh, how the excess pore water pressure gets generated when there is a load applied on a saturated soil. And after that, what happens that uh, slowly that uh, what to say that pore pressure, excess pore water pressure that gets generated gets dissipated slowly as the water gets drained out slowly and steadily. That pore water pressure starts to get dissipated slowly, and then what happens in that time, there is some volume change that occurs in the soil. So that volume change means there is a settlement of the soil layer, you can say like that, right? So we saw that thing in the previous class, and after that we solved some um, problems regarding settlement calculation and all those things. So today what we will be doing is that today we will just be seeing, just revising once what about this all the how the settlement calculation and all those things that we did. We will just revising a little bit, and after that we will be seeing the one-dimensional consolidation equation, right? It is very important one-dimensional consolidation equation. That is one of the basic uh, partial differential equations or basic equations in soil mechanics. So that we will see, and we will see that from the solution of the one-dimensional consolidation equation, what are the parameters we can get it? So how can we get the time required for the particular amount of consolidation to take place? How can we get all those things that we will see in today's session? All right. So all of these things were actually all already discussed in your class, right? All of these things were already discussed in your theory classes. So we will just revise a bit and then start solving the problems. Right. So the derivation of the one-dimensional equation and all those things, I won't be doing that. So I hope those were, means I guess that those were already done in the class, in the normal general classes. So what I will be doing, we will be just revising all the concepts a bit, and then we will start solving the problems. All right. So let us start today's session slowly and steadily. So if there is any doubt during the session, please feel free to interrupt me and ask me anytime. So okay, so just feel free to ask. So let us start slowly. Yeah. So first, what we can see is we have this void ratio versus the effective pressure plot, right? So we in the previous class we saw that from the one dimensional consolidation test or the consolidation test, right, the consolidation test using a consolidometer, how you can get this void ratio versus effective pressure plots, right? So we solved two problems, if I remember, if I can recall, where the data from the consolidation test, such as the providing the tile gauge reading and all those things and the pressure were given. So from there what we did was actually we determined the void ratio corresponding to each of the effective pressure or effective stress or the whatever was the load. So we determined the void ratio corresponding to all of the pressures, and then we and why did we do that? Actually we did that so that we can plot void ratio versus effective pressure plot, right? So initially you can see, say, the void ratio was C naught, then when the effective pressure is sigma 1 prime, at that time the void ratio is E1. Then again when the effective pressure is increased to sigma 2 prime, what happens? The void ratio then reduces to E2. So with increase in effective pressure, actually this void ratio is reducing, right? With increase in effective pressure, the void ratio is reducing. So that's why, if you can recall, we defined a term known as the coefficient of what? Compressibility. Coefficient of compressibility, right? And another one was coefficient of volume compressibility, MB. One is AV and that is MB. So the AV, if you can recall, that AV we had a negative sign there. So the negative sign, why is that negative sign there? Because you can see with increase in pressure the void ratio reduces, right? That's why there is a negative sign there, because with increase in one quantity we are having reduction of the other quantity, right? So all those terms, all this coefficient of compressibility, coefficient of volume compressibility, then compression index, all those things we studied. So right, so already studied, so isn't it? So so we so we'll see. So we, if you remember, we use those terms to in settlement calculation, right? So we will just revising that part also in this class a bit. Okay, so how we use those things like the coefficient of like the compression index and all those things to determine the settlement. Okay, now generally the void ratio versus effective pressure plot actually looks like this standard. This comprises of this void ratio versus effective pressure plots plot that is shown here. This comprises of a loading segment, unloading, and also reloading segment, right? So what is the loading curve? The ABC, if you can see, this ABC is nothing but the loading curve. Okay, so as we reach the point C, what is done is that the load is reduced, right? Load is reduced, and the CD portion, that is the what? That is the unloading curve. Okay, now if you see this a little bit properly, you can see at this point, say this D point, now the void ratio is, say, this E2. Okay, but at the same effective pressure before, while the while we were initially when the loading was there, at that time it was, say, E1. So obviously you can see this E2 is obviously lesser than E1, right? So that means what? Even if we reduce the load, the soil already has undergone some permanent deformation. Okay, some permanent deformation is there. It does not go back to E1 again. Okay, now it only gets back to E2 void ratio. All right. So again, what we do? Again, we load. So this curve EFG, this EFG is nothing but the reloading curve. Okay, and if you observe properly, the reloading curve has a flatter slope. Okay, this reloading curve, the initial reloading curve from here, you can say to here. Okay, this portion has the slope is little bit flatter. Okay, in this region, the slope is little bit flatter, and the in loading portion you can see the slope is quite steep. And then again, as we cross the point C, okay, as we cross the point C, so you can see the curve is again getting more steeper. The FG point is that this FG curve that you see, that FG is quite steep, right? Which is quite steep. So this is how the void ratio versus pressure plot actually looks like. Okay, this is how a general void ratio versus pressure plot looks like. Now, what is pre-consolidation pressure? The pre-consolidation pressure is the maximum effective pass pressure. Okay, the maximum effect pressure that the soil is undergone in the past. So see, so now see, if in this graph, if we notice what we are doing, we are loading it up to the C point. Okay, so when we reach the C point, so let me draw it here once. So as we reach the C point, the say this is the effective pressure here. Okay, now what we do, we reload it and load it. So while reloading, say this is the pressure here at this instant, say this is the this point. So at this point, say this is the pressure sigma 2. So now at this point, the soil is, we can say the soil is over consolidated, because what is the maximum amount of stress the soil has encountered in its lifetime? That is this. But now the stress is this. So in all these points, the soil is nothing but it is over consolidated. Okay, so over consolidated. Okay. So what is pre-consolidation pressure? Pre-consolidation pressure is nothing but the maximum effective pressure it is there in the past. Okay. Now there is a graphical method actually to determine the pre-consolidation pressure. Okay, say you have a curve. Okay, say we have this so loading curve for a soil. So for a soil you have this, you got this soil from somewhere and you have this, you tested the soil, and after testing you got this void ratio versus effective pressure plot. Now you want to determine what was the pre-consolidation pressure of that soil, right? So Casagrande in 1936 actually gave this method how to determine the pre-consolidation pressure graphically. Okay, so how to do that? So say we have this, okay, say we have this curve, right? So we have this curve. In this curve, what we need to do first we need to identify the point that has the maximum radius of curvature. So visually we need to identify the point that has the maximum radius of curvature. Visually we need to identify this point. All right, so visually you need to identify that which point has the maximum radius of curvature. All right, so that, so from here what we did was we identified the point A. Okay, we identified the point A as the point having the maximum radius of curvature. Okay, we identified that the point A has the maximum radius of curvature. After we have identified the point A, what we do, we draw a straight line. Okay, we draw a straight line parallel to the effective pressure axis, that is our uh, abscissa, the parallel to the abscissa x-axis. What we do, we draw a straight line AB. Okay, we draw a straight line AB. Now if you notice this curve, now if you see this curve a bit and see that this curve is what I mean, this curve is actually getting attaining a straight portion towards the end, right? Towards the end, what this Mm, yeah. Uh, Attaining a straight portion. So this is GH portion. If you notice, that portion is nothing but a little bit, what to say. So it is going. The curve is coming like that, and at the towards the end, it is getting little bit straight. Okay, that is the GH portion. Okay, so that also we can observe. So what we do is that after drawing the line AB, we draw a tangent at the point A. So at point A, we can draw a tangent. That tangent is nothing but AC. Okay, after we have drawn the straight line AB, what we do, we draw a tangent AC. Okay, we draw this tangent AC. After that, we bisect the line, bisect the angle CAB. Okay, we bisect the angle CAB. So what we will get? So we bisect the angle CAB. So from there we get this angle bisector CD. Sorry, AD, angle bisector AD. We get this angle bisector AD. Right, we get this angle bisector AD. Now what we do, the straight line, we are that portion that we were talking about GH, what we do, we extend this GH portion backwards to meet the angle bisector line AD at the point F. Now the abscissa of the point F is nothing but our pre-consolidation pressure. Okay. Okay, that abscissa will give us the pre-consolidation pressure. So very simple. So we identify the portion of the maximum curvature. We draw a straight line, then we draw a tangent at that point, then we bisect the that angle, then we extend the straight portion to intersect the angle bisector, right? We extend that portion, extend the straight line portion to intersect the angle bisector, and that point where it intersects, that the abscissa of that point, the x coordinate of that point will is nothing but the effective pressure. Okay, so this is how we need to find calculate this. Okay. Okay, now calculation of primary consolidation settlement. Okay, calculation of primary consolidation settlement. Okay, so this thing roughly we have done in the previous class, so just let us just revise a bit of it. Okay, revise a bit of it. So first is when sigma naught dash plus sigma dash is less than equal to sigma c dash. Okay, that means say we have a let me just draw a bit. Say we have something like this. Okay, just roughly I'm drawing, nothing. Okay, and say uh, uh, this point is the effective stress point. Okay, this is the pre-consolidation stress. This is the pre-consolidation stress. Now first case is that initially say my stress was here, and then my stress after increasing, and the stress, this is my, so this is the first case. This means in this part, part actually the soil is over consolidated, and in this part the soil is normally. Okay, so what we do when the soil is actually uh, over consolidated, okay, over consolidated, so the settle in the settlement calculation, so this equation that you see for SC, this is a little bit familiar, right? So we use this equation to calculate what, calculate the settlement in the previous class. But you can see here instead of CC we are using CS. CS is nothing but the slope of the rebound curve. Why are we using the rebound curve? Rebound curve because the soil here is over consolidated. That's why we use the rebound curve. Okay. Now the next case can be this is by sigma naught, and second stage is actually here. So this is the delta sigma bar. Okay, so initially I start from the over consolidated state, but then I cross the pre-consolidation stress and then enter into the normally consolidated state. So first in this portion, what we will be doing, we will be using CS, and in this portion we will be using CC. Okay, CC is nothing but a compression index, right? So you can see that is done here. So here we use CCCS, and in the second part, for the second break, when the stress is here, from here to here we use the CC, and from here to here we use the CS. Okay, and the last is nothing but the both of these are in the normally consolidated normally consolidated portion. So in that case you only use the CC. So this is what we solved in the previous class. Okay, this is what, so we considered that the soil is normally consolidated, right? And then we did this, we solved this. All right, so this is what we did. That's why we use CC for our all the settlement calculations in the previous class, because we considered that the soil is normally consolidated. Now there is one more thing called the secondary consolidation. So main so we discussed three types of settlement, right? The first is the first one is the what? The first one was the immediate settlement, that is the elastic settlement that occurs, that is the immediate settlement. Then we have the primary consolidation settlement, and at the end there is some plastic readjustment of the soil particles. So due to this plastic readjustment, there is some more settlement, very minute settlement, that is nothing but the secondary consolidation. So how to calculate the secondary consolidation? So for that we use this term. Yeah. So see, so here you can see a void ratio versus time scale. Okay. So void ratio versus time scale. So from there, actually, what we do, we calculate the secondary consolidation. So you can see this term C alpha prime. So C alpha prime is nothing but C alpha by 1 plus EP. So what is EP here? EP is the void ratio at the end of the primary consolidation state. Okay, and then what is C alpha in that case? Delta E by log T2 by T1. So we are considering that from time T2 by this, in this time this secondary consolidation is actually taking place. All right, that is what this time T1 and T2 are. And is delta E is nothing but the void ratio, minute void ratio change that occurs in that small in that time period. Okay, so from here to here it's nothing but the primary consolidation, and from here to here whatever like little bit that is occurring, that is due to the secondary consolidation. Okay, okay, just wait. Okay, so next we have the Terzaghis one-dimensional consolidation theory. Okay, so what is Terzaghis one-dimensional consolidation theory? So I won't go into the derivation of this theory, but we will just recall whatever, like recall the basics of whatever has been taught in the class. Okay, so what is Terzaghis one-dimensional consolidation theory? Okay, so the Redzak's one-dimensional consolidation theory is given by this equation, which is nothing but dou u by dou t is equal to Cv by dou square u by dou z square. And what is Cv? Cv is nothing but the co coefficient of consolidation, that is Cv. And what is Cv? Cv is nothing but K by gamma Wmb. K is what is K? K is the coefficient of permeability or hydraulic conductivity. Gamma W is nothing but the unit weight of water, and Mb is the coefficient of volume compressibility. Okay, so this is the very important equation which is known as the one-dimensional consolidation equation. Okay, one-dimensional consolidation equation. All right, so in order to solve this one-dimensional consolidation equation, so this is what this is. So this is a partial differential equation, right? This is a partial differential equation, right? The partial differential equation where there are where the independent variable or the dependent variable are what? The u. What is u? U is the pore water pressure, right? Is the excess pore water pressure, that is u, right? Or the pore water pressure, that is u. And what are the independent variables? Are t and z. T is the time and z is the distance, right? There is the distance that you can see in the figure that is given here, that is z. So what are the boundary conditions that are actually necessary in order to solve this problem? So let's see. The boundary conditions are at z equal to 0, u is equal to 0, and at z equal to twice h dr, we have u is equal to 0. That means that this point and this point u is 0. So if you remember the previous class, as we had discussed, if you recall, the u becomes 0 at the because see we have a clay layer which is sandwiched between two drainage layer, that is two sand layer. Sand is the drainage layer, right? So here we have the condition of double drainage, because from both the sides, both the top and bottom of the clay layer, the water can drain out. So it is a condition of double drainage. In double drainage condition, at the top immediately see the water can drain out, at the bottom immediately the water can drain out. That's why the pore water pressure, we are saying that at that point the pore water pressure is 0. Okay, and at one more condition is that when the time is 0, the pore water pressure that is going to exist all over the layer of the soil, that is nothing but at t is equal to 0, u is equal to u naught, u0. Okay, u is equal to u0. Now if we use there are many methods. Okay, there are many methods which are actually used, which can be used to solve the partial differential equations. So if we use the method of separation of variables and try to solve this consolidation equation, what we will be seeing is that we will get a solution something like this. Okay, you will get the solution something like this. So in this solution, a term which we have to give importance to is this TV. This TV is nothing but the time factor, which relates how much time, okay, how much time the uh, pore water pressure dissipation is going to take, where the how much relates to how much time the pore water pressure dissipation is going to take, and that means it also relates to the amount of consolidation settlement. So in say it relates to at what time how much amount of consolidation settlement is actually going to occur. Okay, it relates to that. That's why it's known as time factor, because it relates time to the amount of consolidation that is going to happen. That is a degree of consolidation. Okay, that's why this is known as the time factor. And one more thing, if you see here what is the drainage path? So here the drainage path is nothing but HDR. Okay, HDR, because it is the case of double drainage. So so water particle that is here, water molecule that is here, it will have to travel a maximum of HDR distance to drain out. That's okay. That's why the drainage path here is HDR. All right. Now, as I said, TV is the time factor. TV is the time factor, and that TV is given by this particular expression. So you can see here this TV relates to the time t, directly relates to the time t, and this TV is non-dimensional. That is, it doesn't have any units. Okay, TV is non-dimensional. That means it doesn't have any unit. So what does the TV do? This TV actually relates to directly to the time. Okay, directly relates to the time. Okay, what is CV? CV is the coefficient of consolidation, and HDR is nothing but the drainage path. Okay, so the degree of consolidation at any depth z at any time t is uz equal to 1 minus uz by u naught. That is nothing but u naught minus uz by u naught. That is what? The initially what pore water pressure was there, now what pore water pressure is there, divided by initially what pore water pressure is there. That right, that will give us the, so this will keep on reducing, right? This will keep on reducing. So the, so that's why from this expression what we can get, the degree of consolidation, how much consolidation has occurred. So you can see usually is nothing but the excess pore water pressure at time t at the depth z, and you notice the initial excess pore water pressure, the initial pore water pressure. So if the degree of, capital U, if the degree of consolidation is between 0 to 60%, then TV is given by this expression. Okay, please remember this expression. These are very, very important. Okay, please remember these expressions. If the degree of consolidation is between 0 and 60%, then TV is given by this expression. And if the degree of consolidation is greater than 60%, then TV is given by the other expression. TV is equal to 1.781 minus 0.933 log 100 minus u%. Okay. Now let us see the graph, that is plot that is given here. So you can see here we have plotted Z by HDR. Okay, and at the bottom you have plotted a degree of consolidation, right? Degree of consolidation. Now, now, now when the time is very less, that is TV is 0. So directly it's relating, TV directly relates to time, right? So when time is 0.1, very less time is elapsed. Very less time has elapsed. So you can see here at the bottom the degree of consolidation is very less, but at the top and the bottom means this is the clear layer, right? So middle and top and bottom we are considered. So at the middle degree of consolidation is very less, but at the top it's always 100%. But that is what we have assumed, right? Because at the top and bottom we have assumed that this pore water pressure is 0 always, right? So as time increases, that means as time factor is increasing, we can see that the degree of consolidation is also increasing at the middle portion. Okay, so finally you can see for time factor equal to 0.9, you can see at the middle almost 90% consolidation settlement is occurred. Okay, okay. So with increase in time factor, the amount of consolidation that is taking place at all the points, that is also degree of consolidation, that is also increasing. So what is happening actually as time passes, it means a time factor is increasing, means time passes. As time passes, time factor is increasing means what? Time passes. As time passes, the pore water pressure gets more and more dissipated. That means more and more consolidation is happening. That's why we are, the degree of consolidation at the point chart is keeping on increasing. Okay. Okay. So that is how here TV is also related to the degree of consolidation at any z, depth z. Okay, so all the depths will have different degree of consolidation at a particular time. Okay, so using this all these relations and keeping all these factors in mind, what we will be doing is that we will be solving some problems today, and we will be seeing how actually these things come into play. Okay. So let us start. Okay, let us start. All right, so let us start. Let us start solving the problems. The first problem is for the soil profile shown in the figure. The soil profile shown in the figure, initially water table is at 5 meters below the ground level, which is lowered permanently to a depth of 15 meter below the ground level by pumping over few years. All right, so initially the water table was at a depth of 5 meters, and then the water table gets reduced. Okay, the depth gets lowered to 15 meters due to pumping over the few years. Assuming unit weight of water is 10 kilonewton per meter cube, unit weight of sand of the water table is 18 kilonewton per meter cube. Unit weight of sand and clay below the water table equal to 20 kilonewton per meter cube, and coefficient of volume compressibility is 0.25 meter cube per meganewton. Determine the settlement of clay in mm due to lowering of the water table. So what we have to do is that, so here we have a mm, clay layer that is there. Okay, clay layer is present here, and above that we have sand layer. Okay, that is the drainage layer. So initially the water table is at a depth of 5 meters, right? And then due to the pumping, what happened, the water table got reduced to 15 meters depth. Okay, depth of the water table increased, that is the uh, okay, it go the water table got more below, right? So what will happen actually? What do you think is going to happen due to this water table lowering? What effect does it going to have? What do you think? What effect do you think this water table lowering is going to have on the soil? So obviously, what is going to happen? Due to this lowering, the effective stress on the clay layer, the effective stress is going to increase, right? The effective stress is going to increase, isn't it? The effective stress is going to increase. So this increase in effective stress due to the lowering of the water table is going to induce some consolidation settlement. All right, this in this lowering of water table is going to increase the effective stress on the clay layer. So due to this lowering, what is going to happen? It is going to induce some consolidation settlement in the clay layer, and that consolidation settlement of the clay layer due to this lowering of water table due to the increase in effective stress, that you need to find out. Okay, that you need to calculate. All right, so let us find it out. So initially, let us calculate the uh, effective stress at this point, right? Initially, let us calculate. What? 5 into what is given above water table, it's 18, right? 18 plus 5, then we have 15, so this is 20, so this will be 15. 15 into 20 minus 10, that is the submerged unit weight, plus 2.5 into 20 minus 10. So please calculate this. Please calculate this. So this will come out as, okay. Now let us find out, due to the lowering of the water table, what is the, due to the lowering of the water table, what is the effective stress? Okay, due to the lowering of the water table, what is the effective stress? Let us see. 15 into okay, so calculate this. So this will be, so due to the lowering of the water table, the effective stress gets increased from 265 to 345 kilonewton per meter square. Therefore, it is the increase in effective stress. It's 345 minus 265. Right, so now what is delta H by H naught? So what is AV? Delta E by delta this. So delta E generated by AV, and AV by this is nothing but MV. So therefore, what is the settlement? H naught into MV into the stress, right? So H naught you put 5 meter, M is 0.25 into 10 to the power minus 3 into, understood, right? Y minus 3 understood, right? So mega Newton, I am converting to kilo Newton, and this one to 80. So this will come out as, okay. So quite simple only, right? But it's important to understand this basic concept that this problem is going to make you learn, that is lowering water table will induce increase in effective stress. That increase in effective stress will induce a consolidation settlement. Okay, that is the important take from this problem. Okay, that is the most important take from this problem. Okay. Okay, now let us see the next problem. find the settlement of both the clay layers. Okay, so here we have two clay layers. Okay, two clay layers are there between sand layers, and 150 kilonewton per meter square we are applying some extra load. So we need to find out the settlement in both these clay layers. Okay, so first let us do for the layer 1, and then we will do for layer 2. Okay, so first let us do for layer A. Okay, so what we can do, so also one thing, so you can see water table is here, right? So water table is at the top, so everything is in a submerged condition, right? Everything is in a, all the layers are submerged condition. So first let us we can do is, then let us find out the submerged unit weight of these clays. Okay, so what is it's given minus 1 by 1 plus c wg. What is w? So calculate this, how much is it coming? Okay, so now let us calculate the effective stress at the layer A, at the clay layer, at the middle of the clay layer. Okay, at the point, at the level AA, at the AA level, let's calculate. So 6 into, calculate this. Let's calculate. Just a second, let me check something. Yeah, so this will be, okay. So therefore the settlement you can find out, right? What is cc? E naught we are taking as this w into g. Okay, okay, so calculate this, please calculate. Let us see how much settlement we are getting for this layer, and then we will see for the lower layer how much settlement we are getting. Okay, this will come as 0.2. Okay, that was for layer A. Now let us come to layer B. So layer B also, this gamma everything will be same only, because you can see the G is same, W is same, everything is same, right? So gamma, this how much unit weight is going to be, unit weight is going to be the same. So just let us first calculate the effective stress. So 6 into 3 into 8.02. So calculate this. This will be mm, right. Therefore, similarly, what we can do, we can find out settlement. Then so less settlement is going to occur here, right? Obviously, because the change in stress is very less. So here we will get 11.42 C. Okay. Therefore, total settlement. Okay. So that's it. So very quite simple only, right? Now let us see this. An odometer test is performed on a normally consolidated. An odometer test is performed on a normally consolidated clay stratum that is 350 centimeters thick. That is 350 centimeters thick, and is found that the clay's initial void ratio was 0.8 and its primary compression index is 0.28. The in situ stress at the mid clay layer is 120 kilonewton per meter square, and the secondary compression index is 0.02. The building exerts a pressure through its mat foundation of 80 kilonewton per meter square. The time of completion of primary settlement is approximately 18 months. What is the total consolidation of 350 centimeter clay stratum 5 years after the primary consolidation? Okay. All right. So what we need to do here is that first, uh, 5 years after the primary consolidation has occurred, we need to determine the consolidation that is taking place. So that consolidation which takes place after the primary consolidation, that is nothing but our secondary consolidation, right? So 5 years after the primary consolidation has occurred, we need to find out how much uh, consolidation has taken place, right? This total consolidation finally we have to find out. So in 18 months we are getting primary consolidation is complete, and after that 5 years some amount of secondary consolidation is going to occur, and so total we are going to add that up and find out the required settlement after the mentioned period of time. Okay. So first what we can do, first let us find out the consolidation settlement. So what is the consolidation settlement? You already know that. Right. So what is CC? CC is given H naught. What is H naught? 350 centimeters. Initial void ratio is given 120 plus 80 by 120. Okay. So this will give us a. So calculate this please in 1 minute. Fast, fast, fast. Please calculate. Calculate and let me know what the value is coming. So this is coming out as 12 point. Okay. Now let us calculate the secondary consolidation. Now, secondary consolidation has a uh, similar relation, right? But here what we will be doing is that we'll be, let me just write the now this H100 is nothing but the height or the height of the or the height of the or the thickness of the clay layer at the end of the thickness of the clay layer at the end of the primary consolidation. E100 is the void ratio of the clay layer at the end of primary consolidation. Okay, all these things we have so 800 we already can find out from the by deducting the total deducting this SC from the total thickness of the clay layer, right? That we can how to determine in E100. So E100 is what? E100 is nothing but the initial minus the delta E. It is the at the end of the primary consolidation, means how much whatever change is happening, right? So in order to do that, what we'll do, we will just use the same relation. Okay, understood? So we will use this relation. All right. All right. So what is CC? CC is nothing but the slope in the E versus log P graph. log sigma graph, right? That is CC. So from there you can write this thing we can write, isn't it? This thing we can write. So now let us do, right? I hope this is clear to you. Okay, understood, right? Just using the basic definition of CC we are writing this. What? This is delta E. This is, so this is what? CC. The slope is CC. So using that we are writing this. So this will give us, right, E100 we got, and H100 we can find out from what? 350 minus 12.08 will give us 337.92 centimeters. So E100 we got, H100 we got. What is T? What is T? T is 5 years. So in the question, if we see, we are asked after, sorry, extremely sorry. Yeah, we are after 5 years after the primary consolidation, what? So that is T is 5. And what is T100? T100 is 18 months. 18 months means 1.5 years. So that is T100. So now we'll plug all those things in our equation. So equation CS, what is CS? CS is 0.02. H100 is 337.92 and plus 0.73 E100 into log 5 years by 1.5 years. So this will give us 2.04 centimeters. So you can see this is quite very less compared to the almost how much, quite less, very less compared to the consolidation settlement that is occurring in 1.5 years. Therefore the total settlement SC plus SS 12.08 plus 2.04 plus 40.12. Okay, so hope this is clear, right? That's the basic expressions, the basic concept we are using. Okay, now let us see this problem. How many days would be required by a clay stratum 6 meter thick, draining at both the ends with an average value of coefficient of consolidation of this much? Coefficient of consolidation is given to attain 50% of his ultimate settlement. Means time required to attain 50% consolidation settlement you need to occur. So please try to solve. I will give you 2 minutes. Please try to solve this by yourself. Just use whatever was discussed in today's class, whatever concept regarding time factor and all those, whatever relations were discussed in today's class, use those relations to solve this problem. Okay, that is the hint. Use the relations of time factor and all those things that were given to you in this class. Okay, use those to solve this problem. So just try for 2 minutes to solve this problem. Just try by yourselves. Just try by yourself for 2 minutes. Just try. It's very simple. Please solve. Very easy. Everything is given to you directly. Everything is just given. Just you have to use the correct relation to find the solve the problem. Okay. CV. First, what is the thing that is given to CV? What is the coefficient of consolidation? It's the first thing that is given. Next thing, what it is it is asked that to attain 50% of the ultimate settlement, means when the degree of consolidation is 50%. This means what? This means when the degree of consolidation is 50%, we have to find out how much or how many days will it be necessary to attain that, right? So degree of consolidation here is 50%, that is given. Now what is the relation between TD, it is a time factor, and degree of consolidation? If the degree of consolidation is less than 60%, what is the relation? TV is equal to pi by 4 100 square, right? So pi by 4, what is u? 50 by 100 square. So this will calculate this. This always you should remember, this is 0.197. Okay, very easy to remember. For fast calculation, you can remember this 0.197. Now you know this TV, this is T50, T at 50% consolidation is 0.197. Now you write the relation between TV, CV and T. Is CV T by H drainage square. Right? Right? So from here, what is T50? 0.197. CV is 50 into 10 to the power minus 4. T50 we need to find out. And what is H drainage? What is H drainage? So here draining at both the ends, and a double drainage. Double drainage means half of the thickness will be the drainage path. Half of the thickness of the layer will be the drainage path, because it is a double drainage case, right? So 3 meters. So 3 meters means 300 centimeters, so 300 square. So from here if you do, you will get T in seconds if you get. So convert that to days and tell me the value, please. How many days? Convert the seconds value to days value and please tell me. So this is going to come out as 0.04 days. So you can see for 50%, attaining 50% of the ultimate settlement, it is for 50% consolidation, it is going to take 41 days. Okay, in 41 days we are going to achieve 50% of the, we are going to achieve 50% of the ultimate settlement. Okay, in 41 days. So very simple, right? Direct going to use the relation and find it out. Let us see this now. A soil stratum is 10 meter thick with pervious stratum on top and bottom. Means what? Means double drainage. Double drainage case. Right? 10-meter thick stratum is the top and bottom. We have pervious stratum in double drainage case. Determine the time required for 50% consolidation. Given K is given to you, AB is given, and E void ratio is given. So coefficient of consolidation is not given here, right? What is given to you instead? Coefficient of permeability is given to you. Coefficient of permeability is given to you. Or hydraulic conductivity is given to you. Hydraulic conductivity is given to you. Coefficient of compressibility is given to you, and void ratio is given to you. Right? So similar problem, just try to calculate. Very easy. Just try to calculate similar to the previous. Just different values are given now. So K is given, AB is given, and E is given. Okay, find out what is find out the necessary values. What? The first necessary thing that you need to calculate is what? The first necessary thing that you need to calculate is coefficient of consolidation. So find out coefficient of consolidation. Recall the relation and try to find out the coefficient of consolidation. Find that out, please. What is CV KY MB into gamma W? What is MB? AB by 1 plus Z naught. So 1 plus E K AB gamma W. So put the values and find out CV. Gram and cm, right? So we are, let us put in gram per cc. So really one, so find it out. Right? I hope you are getting this 10 to the power minus 3 centimeter per second. Okay. Now you know CV. Now just use the same thing that you did in the previous problem. So T50 you know already from the previous problem. You already calculated it's 0.197. So now use that same relation. What is HDR square? Double drainage, right? So 10 by 2 5 5 square 500 square. Find this out. It will come in seconds. Convert to days. Let us see how much it is coming. It will come to. So you can see here in the previous problem, uh, it was 10. The coefficient of where is it? Yeah, leave it. We can no need to compare. Okay, leave it. Just I want to say that there larger number of days are actually required because the CV is reducing by 10 times. Okay, you can see the CV is 5 into 10 to the power minus 3 centimeter square per second. Here it's 10 to the power minus, means by 5 times the CV is reducing. It means obviously the K is also going to be less. In the previous case, whatever, if you compare, if you calculate the K and check, you'll see that the in present in this case the K will be more lesser. So more lesser K means the more slowly the water pore water pressure is going to get dissipated. That's why more time is it's taking to attain 50% consolidation. Okay. Now next problem, a homogeneous clay layer 12-meter thick is expected to have an ultimate settlement of 322 mm. After a time span of 3 years, the average settlement was measured to be 152 mm. Okay, the homogeneous clay layer 12-meter thick is expected to have an ultimate. So ultimate settlement is given to you. Okay, but 12-meter thick layer, sorry, the ultimate settlement that layer is going to have, that is given to the ultimate. That is 322, means 100% settlement is 322 mm. After a time span of 3 years, the settlement it has occurred is 152 mm. Okay. Now it is asked you how much longer will it take for the average settlement to attain. So for 152 mm settlement, 3 years you are taking, and we need to find out for 237 mm settlement how much more time will it be required. Okay. So how to do that? The first, let us write down the degree of consolidations. Okay. In first case, the degree of consolidation is the total settlement. Settlement by total settlement, it is, so this much is the degree of consolidation in 3 years time. This time we don't know, that we need to calculate. Okay. So this is less than 60%, right? It's less than 0.6, less than 60%. So for u1 u less than 60%, what is TV? Therefore TV1 square. So this is going to come out as 0.175. Okay, this is going to come out as 0.175. All right, understood, right? Understood. We use the relation for TV and U. Okay, we got TV1 as 0.175. Now from there we can write. So from here what we can do, we can find out CV. So isn't it? This, or what we can do, we can let us write this as CV by d square. CV by d square, let us keep it like this. This will be TV1 by T1. So TV1 is what? TV1 is 0.175, and T1 is 3 years, equal to 0.0583. So this we got. This we got from the first case that is given to us. That this one we got. Now we are seeing that for the second case, for 237 mm means 73.6% settlement has occurred. That is greater than 60% settlement has occurred. So now we cannot use this relation. We will use the other relation for this. So TV2 right. So from there, please find out TV2. It will be Now use the same old relation again. Cv by d square I can keep, I know already tv2 I know, so t2 will be not, t2 is what? This will come out as 7.8 years. Okay, that means in 3 years, in 3 years 152 mm settlement occurs, and in 7.8 years 200 and how much is given, 237 mm settlement occurs. That means delta t is, means after 152 mm settlement 5.8 more years, so not 5.8, 4.8, 4.8 more years are actually required to achieve total of 237 mm settlement. Okay, the problems are quite simple. Directly you have to use the part relation and find it out. All right, let's see the next problem. At a given site A having a clay layer 8 meter thick with single drainage, remember single drainage, a uniform fill that was uh, constructed, okay, resulted in a settlement of 5 centimeter in 1 year, corresponding to 50%. Okay, it means 5 centimeter settlement is occurred in 1 year, and that 5 centimeter settlement is the 50%, 50% settlement. Okay, 50% reduced consolidation. It was found that a neighboring site, the same type of clay exists but having a different thickness. Okay, now the thickness is 18 meter. How long will it take for 50% consolidation occur, and what will be the magnitude of the settlement if the field of the same magnitude? Okay, same fields, right? Same field. Okay, so let us see. So what is T for 50%? It's 0.197. CV I don't know. T in is 1 year, and single drainage, right? So 8 square. So CV from here I will get it as 12.608 meter square per year. Okay. Okay. Now this is for A side. Now for B side, the thickness is, so HA was what? Thickness was 8 meters, right? This is the thickness. Okay. Time T50A is 1 year. Okay. And delta HA in 50% is 5 centimeter. Okay, this I know. Now for B, what is the thickness of B layer? It's double 16 meter, right? So now again let us use the TV same relation. TV for 50% is 0.197. CV, say the soil is same, right? The field soil is same, so same CV I can use. What is D? 16 square. So from here T will be nothing but 4 years. So you can see 4 times, right? So for here, for the layer A, for the layer A, for the layer, so the site A, in 1 year 50% settlement is occurring, but inside B, where the thickness is doubled, where the thickness is doubled, and what is happening? Where the thickness is doubled, my time is getting quadrupled. Right now, from 4 years will be required for 50% settlement. All right. And also one more thing is asked in the question. It is asked that what will be the magnitude of the, so initially for the first soil it is given 5 centimeter in 1 year. Now I need to find out in 4 years, it is 50% consolidation time, what will be the 50% consolidation for the second layer for this side B. So for that what we can do, see, we can write this delta H is what, MB H not. Now see, MB is constant for a particular type of soil, so here both are same type of soil, so MB is constant. This increase in stress can also be considered constant. So for that case I can write, isn't it, from here I can write 5 by 16, from here to be 10 centimeter. So this is what, this is settlement, this is delta H50 for B. Okay, and this T50B is 4 years. Okay, so now if I write HA, how much, 8 meter, delta HA in 50% is 5 centimeter, TA50 is 1 year, HB is 16, delta HB50 is 10 centimeter, TB50 is 4 years. Okay, so this is the final answer. Okay, so quite simple, only very simple. Now let us look at the next eighth problem. A settlement analysis carried out for a proposed structure indicates that uh, 5 centimeter of settlement will occur in 5 years. Okay, 5 centimeter settlement is going to occur in 5 years, and the final settlement, is the ultimate settlement, will be 25%, 25 centimeter. Okay, that means 20% settlement is occurring in 5 years, right? 5 by 25, 20% settlement is occurring in 5 years. The computation was made on the basis of double drainage condition. However, subsequent borings established only single drainage condition. Okay, so 50% consolidation is 20% consolidation is occurring in 5 years if it is single drainage consolidation. Now in the same 5 years, how much settlement is going to occur if we are having double drainage? Okay, now in the same time, if the drainage condition is changing, from initially it was single drainage, now it becomes double drainage, so obviously in 5 years time, the same time, more amount of settlement, before it was 25 centimeter settlement, now that amount of settlement is going to increase. That we need to find out how much settlement will occur in this case. Obviously it is going to be more than 5 centimeter. Okay, it is obviously going to be more than 5 centimeter. Before 5 years 5 centimeter had happened, but now we are seeing that it is double drainage condition. So in double drainage, obviously in 5 years more than 5 is going to happen. So what is that we are going to find out. Okay, so 5 centimeter is happening in 5 years. Okay, so what is U1? Right, because less than 60%, so that's why we are using this relation. So this will come under 0.0314. All right, and in this case what is the drainage? Drainage is double drainage, single drainage, right? Here it is single drainage. Okay, single drainage, single drainage. Now let us use the equation. T is equal to CdT by HDR square. So 0.0314 into CV into what is the time? 5 years by drainage DR square. So CV by HDR square, we are going to have 0. So 0.0314 divided by 5. Okay. Oh, sorry. I was telling. Okay, sorry. So I got the question wrong. That's why I was thinking. Okay. So in the so okay. So five. So far initially the calculation was carried out on the basis of double drainage condition. Okay, that means in 5 years, 5 centimeter settlement will occur if the condition is double drainage. If the condition is double drainage, not single. This is double drainage. Okay. Now, now it is told to us that if it was established later that single drainage is occurring. So if single drainage occurs, so in 5 years now less than 5 centimeter settlement will occur. Less than 5 centimeter settlement will occur. So that less amount we need to find out how much settlement is going to, right? I was getting actually opposite thing in my mind. Sorry for that. Extremely sorry if I have confused you. Extremely sorry. So the first case was double drainage. Second in single drainage condition. Okay. So say you have thickness d. So the layer thickness is d. So HDR in this case will be d by 2. So d by 2 square to d by 2, and this is HDR. So first is the double drainage case. So 4, so 4, so 5. So from here CV by D square is coming out as, okay, so D is the complete thickness, okay, thickness, and for double drainage and the HDR is known as a drainage path. So first case is double drainage. Now for single drainage, for second case it is the single drainage. That time T is same, 5 years, right? 5 years. Now for single drainage, so initially say how much percent? 20%. Now obviously less than 20% is going to occur, so you can safely use this relation. Okay, now this is equal to what? TV is equal to CV T by D square, you can equate to this. Now single drainage. So if you put, so if you write this again, CV into 5 by HDR, what is HDR? Now HDR is equal to D. HDR is equal to D. Here HDR was equal to D by 2. D by 2, but now it's equal to D, to D square. So pi by 4 u square, CV by D square, we know this value. We can put this value. So from here, if you solve this, you will get U as 0.1. So therefore, if the, now that is 10%, so before 20% settlement is occurring, so 10%, now half settlement will be occurring. So H2 will be nothing but 0.1 into 25, it is 2.5 centimeters. So in double drainage case, we are having in 5 years 5 centimeter settlement. But now for single drainage case, we will be having in 5 years 2.5 centimeters. So half. The settlement is reduced by half. If drainage path is reduced, doubled. If drainage path is doubled, if the length of drainage path is doubled, from it is before it was double drainage, the path length was d by 2. Now it is d. So right. So in that case, what is happening? The if the drainage path becomes from double to single, the settlement will become half. Right, and vice versa. Got that? Okay. Very simple. So please see this problem. Now, a clay layer 8 meter thick is subjected to a pressure of 70 kPa. If the layer a double drainage and double drainage, if the layer double drainage undergoes 50% consolidation in 1 year. Okay, double drainage condition, 50% consolidation in 1 year. Determine the coefficient of consolidation. If the coefficient of permeability is given, determine the settlement in 1 year. So we need to determine the uh, coefficient of consolidation and also the settlement in 1 year. Okay, so please try to do this by yourself. Just try to think once. I will solve this obviously. Just try to think by yourselves how we are going to approach this problem. Just try to think once. Very simple. It's actually very simple. Just try to solve. See. First, what is written here? See. U is how much? 50%. U percent is 50%. That is happening in 1 year. And the double drainage condition. Okay, double drainage condition is there. Alright. So double drainage condition is there. What is the drainage path? Clearly is 8 meter thick. So D by 2, 8 by 2, 4 meters. Now TV is equal to CVT by HDR square. So CV you can find out from here. TV time is 1 year. So this will CV will be okay. Easily we calculated CV. Now if the coefficient of permeability is given, okay, the coefficient of permeability is given, you need to determine the settlement. Okay, settlement in 1 year. So in 1 year we know this 50% settlement is occurring. So remember this. We'll use this. In 1 year 50% settlement is occurring. So let us calculate the ultimate settlement that we are going to have. The ultimate at t is equal to infinity. Okay, ultimate settlement we are going to have. So for ultimate settlement, we know that the ultimate settlement is given by what? Right? So for that we need MV. So for this we need MV. So MV, how we can calculate? So from CV you can calculate, right? So what is CV? So from here, MV is what? KY CV into W. So K is given to us, right? Coefficient of permeability of hydraulic conductivity is given to us. So 0.040. This we calculated just now here. Here we calculated this into 9.81. It's going to come out as 1.3 into 24 minus 3 meter square per kilonewton. Okay, so MV you know now. Now 1.3 into 10 to the power minus 3. What is the increase in stress pressure? 70 kPa. 70 into what is the thickness of the layer? 8 meters to 8. Put. So it is asked to us determine the settlement in 1 year. So in 1 year, 50% consolidation takes place. Therefore, settlement at t is equal to 1 year is 50 by 100 into nothing but 0.36. Okay, I hope this is clear, right? Okay, let us come to the 10th problem now. For the given arrangement, find the settlement by dividing the clay in 4 layers. So you can see in the image the clay layer, the total clay layer is divided into 4 layers. Okay, and there is a footing in which 225 kilonewton load is actually coming. So what we need to do, we need to do two things. First, we need to calculate the effective stress at the center of all these 4 layers. Okay, and then what we need to do, then we need to determine the increasing stress from coming from the footing at the center of each clay layer. Just try to do this, then I will solve. Just try to do for first layer. Please try to do at least. I will give you 2 minutes. Just for first layer, try to do by yourself once. First, try to do that at least for the first layer. For layer one, try to do that. Quite simple actually. Please try to solve. Actually, quite simple. We have solved similar problems, right? We have solved same many of the problems, similar problems. So I think it's quite easy only. For you should be quite easy for you. So please try to solve. See. So first, what did I say? First, let us calculate the effective stress, right? So it is everything is given to me, right? Gamma and all everything is given. So what I can do, so this is 1.5 and the center here, right? We are finding out here the middle of the layer 1. Okay, middle of the layer 1 we are finding out. So 0.25, so 1.75. Okay, next step is increase in pressure. That also you know how to find it out. Okay, right, right. This is n is what? It is given 2 horizontal, 1 vertical, so n is 2. Okay, 2 horizontal is to 1 vertical, then 2 from 2 sides it will come to 2 into 25, so this will come out as 36. So please check all this, okay, from once. If there is any mistake, please let me know. Please, if there is any mistake in these things, please let me know. Please check yourselves everything, please do yourself, and if you find any mistake, please let me know, isn't it? Okay, why 0.25? Because from here to here it's 0.25, right? Right, hope you understand. Right, so 0.25, this is 0.25, this I want to know, right? So 2 horizontal to 1 vertical. So horizontal I don't know, vertical I know. 2 into this side, both sides will have that part. So this one I hope you understand. This comes to 36 km per meter square. Right? Therefore S1 will be, so CC is what? H is 0.5. Correct? So this will come out as, okay. So this one you understood, right? So this is there, right? So this is, you are distributing it like this. So at a depth of 0.25. Okay, so this is what? This is 2 into 0.25, and again from here 2 into 0.25, and plus this is the width 1.5. Okay, so that's how we are doing it. Okay, now again for layer 2 let us do same. Layer 2, what will be this gamma 2? So what is the height? 1.5 into 2.2 2.25 into 20, isn't it? 2.25 into 20, so 45 delta sigma 2. What is the depth from here to here? 0.5, 0.75. So it's 2. Okay, similarly layer 3. Okay, layer 3 will get S3s. So do this yourself. Okay, I am giving you the answers, just do this yourselves and see if you are getting the same values, and for layer 4 you will get, okay, therefore total settlement is S1 plus S2 plus S3 plus what is 9 mm. Okay, so do this yourselves and check the values. So do yourselves and check. Okay, do this. All right. So done. Very simple, quite simple. Like whatever we did in the previous class, and today also we some more similar problems. Done. Let us go to the next problem. A saturated soil strata 6 meter thick lies above an impervious stratum and below a pervious stratum. Okay, saturated soil stratum 6 meter thick lies above an impervious stratum and below a pervious stratum. Okay, it has a compression index of 0.28 and a coefficient of permeability of 3.5 × 10⁻⁴ centimeter per second. Its void ratio at stress of 150 is kPa is 1.95. To determine the change in void ratio, the stress is increased from 150 to 210. Okay, that we can easily find out, right? Settlement of the soil stratum due to the above increase, that also easily you can find out. Time required for 50% consolidation, take T is equal to 0.2. Amount of settlement which will take place in 1 hour, the ultimate settlement of the stratum. Okay, let us do step by step. Okay, one by one let us try to solve. So first is change in void ratio due to increase in stress of 200 to 210. So for that we will use the compression index thingy. Okay, compression index thing. So what is CC? Right. So I can write is to CC into this. So what is CC? What is my CC? 0.28. Increased to 210 by 150. This is 210. This is 150. So this will come out as 0.041. All right. So done. So this we found out. Change in the void ratio we found out. Next is settlement of the soil stratum due to above increase in stress. Same thing. All similar thing we will use. So what is delta H? So 6 meter. The stratum thickness. So initially the void ratio is at 150. It's 1.95. So I am writing this 1.95. Even everything is given. Okay. So from here we will get done. Let us come to third one. Time required for 50% consolidation. So time required for 50% consolidation. Now what is relation between time factor and time? So time factor and time, you know, you have this relation, right? We have this relation HDR square. We have this relation. So time factor for 50%, you it is given to take 0.12. This I know. This I need to find out. CV HDR I know. CV I need to find out. Okay, CV I need to find out. For that, to find out CV is the main task. So CV, so what is CV? CV is K by MB into gamma W. So we need to know MB. So MB, for MB you need to know AV. So AV let us find out first. From here we are getting 0.041 by 210 minus 150. So this will come out as 6.83. Okay, and then we have MB. MB is AB by 1 plus E, right? by 1 plus 1.95. So this will come out as 2.32 into 10 to the power minus 4. Check the values. Okay, please check the values by calculating everything yourself. Okay, done. So this we got. Next again we can get CV now. So K, is it given to us? K should be given to us, right? So C, coefficient of permeability is given 3.5 to the minus 4 centimeters per second. Centimeter will convert to meters. So 2.5 into 10 to the power minus 6. So please be careful with the units. Please be careful with the units. If you do mistake in units, your whole answer will come out to be wrong. So please be careful with the units. Okay. All right. So now you have everything. So T we have TV HDR square by CV. So TV is 0.2 into HDR. So uh, uh, so it is a single drainage case. So it is given that lies above a impervious stratum and below a pervious stratum. Okay, so sand. So single drainage. So 6 meter will come directly. So this one will come out as 0.154. So this 0.15. So this uh, so sorry. What did I write? Sorry. This will come out as 1.279 hours. Okay, this will come out as 1.2. So time you found out. Okay. The fourth one is the amount of settlement that will take place in 1 hour. Okay, the amount of settlement that will take place in 1 hour. The ultimate settlement of the stratum was found to be 72 centimeter. Okay, so in 1 hour, for 1 hour, what is the TV? Let us see. Okay, I will do it here only. Okay, just to save space, I will do it here. So TV CV 1 hour in seconds is 306,600 seconds by 6 square. So TV comes out as, that is 1 hour 1.54. So for 1 hour TV is coming out as 0.154. So this is less than 0.197 or 0.2. We are asked to assume 0.2, right? So this is sorry, just give me 1 minute. Yeah, so this is less than 0.2. That means the amount of consolidation is less than 50%. Obviously then it is less than 60%. So we can write from here. If I put all the values, I will get US 44.28%. Okay, now if in 1 hour 44.28% of settlement is occurring, therefore how much settlement will be that in terms of centimeter? 0.4428 times the ultimate settlement, 72 centimeter. That is 31.88 centimeter. Okay, 31.88 centimeter settlement will be occurring in 1 hour. Okay, so this is the answer, right? Now let us come to the 12th and the last problem for today. The coefficient of consolidation of a clay was found to be 0.955 meters square per minute. The final consolidation settlement for a 5 meter thick for a 5-meter thick layer of clay was calculated as 280 mm, assuming a uniform initial excess pore water pressure distribution and permeable layer to be present both below, that is double drainage. Compute the settlement time for 90% primary consolidation and settlement of 100 mm. Okay, so let us do the first thing first. Okay, so CV is given. Now TV time factor for 90% consolidation for U percent is equal to 90% is just use that for relation and find it out. So I will give you direct, it's 0.848. Okay, okay, you can use the relation, you can just remember generally it's 0.197 for 50%, 0.848 for 90%. These two values, I think it will be helpful if you remember these two values. Okay, so 0.848 is the TV for U percent equal to 90% is 0.848, right? Therefore from here T is, you can find out TV. So T 0.848. HDR is double drainage. Double drainage is happening, right? Double drainage is happening. So 5 meter means 2.5 meters. So in terms of mm, if I write CV, what is CV? Okay, mm square per minute, right? So 0.955. So this will come out as 3854 days. That is 10.56 years. Okay. Okay, so 10.56 years are required to obtain time to obtain 90% settlement. So settlement time for 90% of the primary settlement is 10.56 years. So in 10.56 years, 90% of the settlement will occur. 90% of ultimate settlement will occur. Right? Now, for settlement of 100 mm, how much time is required? Let us find it out. So what is the ultimate settlement? Ultimate settlement was 280 mm. So U percent for this we can calculate 100 by 280 is 0.3571, that is 35.71%. So 35% settlement is my 100 mm settlement, right? Right. So now TV, you know, for less than 60%, 5 by 4 into 0.35 square will come out to 0.10015. Okay, therefore T is TV HDR square by CB. So you put all the values, 0.10015 into HDR, what is the drainage, double drainage. Okay, so you put all the values, and CV also you found out, right? Square and CV, what is the CV? CV is given 0.955, will come out as 1.25 years. So for 100 mm settlement, that is for 35% settlement, 1.25 years is required, and for 90% settlement, 10 more than 10 years is required. Okay, done. So actually we can for if we know the soil properties, you can estimate how much time it will require for 109 almost means ultimate settlement, or not, almost 90% settlement to occur, how much time to it will take. So there are various processes actually using it, such as sand drains or prefabricated vertical drains, using which what we can do, we can accelerate this consolidation process. So in short amount of time we can have we can attain the consolidation, so that after that we can construct whatever structure in that over that soil that we want to build. So then later during the service life of that structure, much settlement does not happen. Okay, okay, so we want that even before the construction, we want to accelerate the consolidation process, and so that the consolidation happens faster, and so that in the later stage, after a structure is built over that soil, that structure does not undergo unnecessary settlements, and that might cause damage to the structure. Okay, so this is why this consolidation, this calculation is very important to us. All right, So if you have any doubts, please feel free to ask me anytime, and please check this all the calculation. Please solve this all the problems yourselves once again, so that everything will be clear to you. Okay, just solve all the problems yourselves once again, and if you have any doubt, please feel free to contact me. And the next class will be on 15th of March, same time from 6 p.m. to 8 p.m. The class. So I hope, and before that on Sunday, I hope we will be having one more class. It will be taken by Mr. Shiv Shankar Nandi, and after that on 15th I will be taking one more class from 6 p.m. to 8 a.m. Okay, that will be the 8th class. Okay, so see you on 15th, and thank you so much for attending to this session. So if you have any doubt, please feel free to contact me or ping me anytime. I will be happy to help you. Okay, so thank you so much for attending this session. Thank you, and have a very good day. Okay, thank you.